Okay, this problem asks us to draw a direction field for a given function and to discuss the stability of its critical solutions. Now, using direction fields, they give us a way to see how differential equations behave based off of different initial starting conditions. So, you can sketch arrows on a graph, model different sets of solutions, and to show how its behavior changes over an increasing amount of time. Now to find, it's kind of hard to see. To find, we have to find the critical points. We have given the initial function, and solving for 0 equals 0 gives us y 0, 1, and 3. And they tell us about the direction field that the slope of y is going to be 0 at these points. So we can use that to split the direction field into separate regions, or for later, to analyze the field. Now, one way to draw the direction field is to, using the original function, we can plug in some values here, set up a table of various ones, and to sketch it on the graph, we match the slope y prime at each point on the graph. So for each horizontal line, all the slopes should be the same. The only change would be as you get higher, lower, and vertical axis, you'll notice the slope change. And this gives us sort of a field to see where the regions meet and how they behave as they approach these critical points. So okay, let's qualitatively analyze. We're going to use the function of fy, basic function, plotted y versus fy, and you can see the stability of certain points. Based off of the direction of the slope. So in this leftmost region we see is negative, which will assign a left arrow, and the region of 0, 1, you can see is positive, so that gives us a right arrow. Continuing on, we get a left arrow due to the negative nature, and that we see right arrow for a positive. Now using this, if the arrows converge, that'll mean it's a stable equilibrium. So as you see, y 0, the arrows diverge, which means it's a non-stable equilibrium. And for y 1, the arrows are converging, creating a stable equilibrium. Y 3 is non-stable equilibrium solution, with the arrows non-diverging, the arrows diverging. So the sample solutions, we have here the direction field. The sample solution would be this solid line. See it's bound from 1 to 3. Now in this graph, in this field, the time axis is horizontal, whereas y is vertical. So we can determine the nature of the graph over time by taking limits in each of these 4 regions. We analyze the limits as time goes to negative infinity or positive infinity. And so we split the field into 4 intervals, from negative infinity to 0, we see that the limits, how the limits approach 0 as time approaches negative infinity, and then it will be negative infinity as the time approaches infinity. And so see this for each region, 0 to 1 as the time axis keeps going in the negative direction. It'll approach y equals 0. And as time continues to go on, it'll converge to y equals 1. Now for the region 1 to 3, it's similar, but going in the opposite direction. So as time goes to negative infinity, y will approach 3. And as time moves to infinity, y will approach 1. And for the uppermost region 3 to infinity, time of negative infinity, y will stay at 3, and the limit does not exist as time continues on, because y okay, stop share. Okay, here we have the two direction fields, hand-drawn one versus the computer GeoGebra applet. As you can see, well, it's hard to see the bounds, but there are clear horizontal regions at their critical solutions. So the slope field does match the relative ID